Hello everyone, myself Salar Ahmed from IIT Delhi present on TEM transmission electron microscopy and STEM scanning transmission electron microscopy. These are the content of this video: introduction of TEM, electron source, electromagnetic lenses, condenser lens and aperture, objective lens, resolution in TEM, aberrations, spherical chromatic astigmatism, intermediate lens resolution in TEM, introduction of STEM, TEM versus STEM, CBD in STEM detector. I want make interest towards electron microscopy. Give a brief of electron microscopy. In the evolution of electron microscopy, in 15th and 16th century began making a stride in biology and chemistry. They knew they would need to see more than that naked eyes. Firstly, single-lens microscopes were made by Anthony van Hoek and allow him to see up to 15x magnification in comparison to naked eye. After that, in 19th century, visible light microscope reached their theoretical limit: solution magnification 500x to 1000x and a resolution of 0.2 micrometer. And scientists now use to these advanced microscope and technologies to study the neurodegenerative disease such as Alzheimer, Parkinson, Huntington, as well as cancer, including HIV, malaria, the Zika virus, and many other. This slide shows the milestone in the history of electron microscopy in 1897 to 1986, where in 1931 Max Knoll and Ernest Ruska built the first stem, and after 1986 get the Nobel Prize in this discovery. In this picture show that the discovery of TEM in 1931 invented by E. Ruska, and 1986 Ruska received the Nobel Prize. And this picture see that the Ruska ate the Nobel Prize meet. Let's start the introduction of TEM. Transmission electron microscope is well established and widely used to characterize material. Basically, it provides information on the morphology, structure, chemistry, and even the nature of bonds. A series of problems associated with the material characterization by TEM. The transmission electron microscopy is an analytical technique used to visualize the smallest structure in matter. Basically, TEM is a tower-like structure. Here present electron source, then condenser lens or objective lens, and there see the CCD charge coupled device detector where we see the sample image. Unlike the optical microscope, which is rely on light in the visible spectrum, TEM can be reveal the stunning detail at the atomic scale by magnifying the nanometer structure up to 50 million times. Because electron can have a significantly shorter wavelength, then after this, in this picture, we see that the transfer section of the TEM, it give the clear picture of the lenses and electron source, where is the electron source present and where is the electrostatic or electromagnetic lens is present, where is the specimen is present, and the where is the screen is present. And this is the transmission electron micrograph of SARS-CoV-2 give a nanometer structure with higher magnification in the TEM. In this picture, we see the anatomy of TEM throughout the year in 1980s and 1990 and uh, 21 centuries. The TEM have basically the same design independent of manufacture age. The electron gun, the apertures, the condenser lens, the sample of the viewing screen, and this is the basic idea of the vintage TEM and the modern TEM here. Here I will discuss about the electron source. A reliable source of electron to illuminate the specimen is one of the most important part of the TEM. Generally, three type of electron gun we use in the transmission electron microscopy. Number one is the tungsten filament, and number second is the lab 6, and number third one is the FEG, field emission gun. We see in the picture also, this is the tungsten filament, and this is the lab 6, and this is the field emission gun. I will discuss one by one here. Number one is the tungsten filament. This is a hairpin type heat source we also see in the picture. This is thermoionic in nature. Thermoionic means electron emitted from materials at high temperature. It is the thermionic meaning poor septal coherency. Because electron can be emitted anywhere, like this, like this, like this, from the filament, thereby it has a poor septal coherency. It is a short lifespan, 100 hours, and it is a cheap in price. This is the electron source or tungsten filament. Second one is the lab 6 lanthanum hexaboride. This is also thermoionic, average septal coherency, average brightness, okay life, average price. And third one is the field emission gun. This is also thermionic, good septal coherency, high brightness, long life, expensive in nature. In case of field emission gun, electron can only be emitted from the very tip, therefore they have a good septal coherency. Also see in this picture, this operating temperature of tungsten is 2700, and lab 6 is 1700, and field emission gun is 300. There is a tungsten is a higher melting point than lab 6, and the lifetime of the tungsten is 100 hour and lab 6 is 500, and the field emission is more than 1000. And the crossover size also vary. So here we find that the field emission gun is the most better, but it is a little bit expensive in comparison to lab 6 and tungsten filament. Here we see the resolution through thermionic source and field emission gun. In the thermodynamic source is the resolution is very bad in comparison to field emission gun. This is the 300 kilowatt conventional imaging. Here resolution about 1.7 angstrom, and better resolution in comparison to this one and this thermodynamic source. After discuss about the electron source, I will discuss about the electromagnetic lenses. Basically, an electromagnetic lens is a coil of wire through which a current flow. In electromagnetic lenses intend to focus electron and change the magnification and focus of the uh, beam. Electromagnetic lens composed of basically two major component. Number one is the copper wire coil like this, and the pole piece. Electromagnetic lenses present after the electron source in the instrument. Magnetic field in this coil is asymmetric, weakest in the center and strongest towards the edge. When the electron flow, the magnetic field created around the coil, this field pushed inward into the hole in the center of the lens. This resulting path of the passing electron has a spiral shape. Purpose basically of these electromagnetic lens is same as the optical ones. The change the path of the electron in the desired direction. After that, the electromagnetic lens, we can discuss. We want to discuss the condenser lens. This lens used to form the beam and limit the amount of the current in the beam, and it is also used for control the diameter of the electron beam. The purpose of the condenser lens basically is to focus the light onto the specimen, and the stream is condensed by the condenser lens. Uh, If the condenser current increases, the beam focus well above the aperture, and large part of the beam is intercepted by the aperture. Condenser lens put before the sample, because we shape the image. We effect of this condenser lens, we decrease the beam current and choose the electrons that are more parallel to reach the sample. We, because why you use this condenser lens? Requirement to have a parallel beam for high resolution, protect sample from radiation damage. Basically, we use a condenser aperture is used to reduce spherical aberration, discuss in later slides. In condenser lens, we will discuss about the two type of lenses, the C1 lenses and C2 lenses, which is different function. C1 lenses control the minimum spot size, and C2 lenses control the intensity of the beam. So here we see that in the picture, this is the lens C1, which give the demagnified image of crossover. After discussing the C1 lens, discuss about the C2, the second condenser lens. Basically, we use the C2 lens to produce the size of the illumination of the screen. When we focus the C2 lens, we enhance the intensity but damage the parallel beam setting. Here we see that from the picture, when C2 lens is focused, give the front focal plane of the objective lens, and this give the parallel beam, and in under focused give the un, under focused beam, not give a parallel beam. After condenser lens, I will discuss about the condenser lens aperture. In the condenser lens aperture, control the fraction of the beam which is controlled to hit the specimen. It therefore help to control the intensity of the illumination. Here I will also discuss lens C1 and lens C2, but here I will discuss about the aperture. When the aperture is widened, the gun crossover is 50 microampere, and spot size of first crossover is 30 for microampere. Spot size at the specimen 65.75 microampere, and beam crossover is 27. This is the probe is here widened and less diffracted and give a big spot on the screen. In this picture, we see that there is the aperture is narrower and give a sharp ray of the electron on the specimen and give a more diffraction and better diffraction. Here gun crossover 50 microampere, sport size first crossover 34 microampere, sport size specimen 50.3 microampere, beam crossover here is 12. In case of objective lens, which is put after the specimen, the most important lens in the TEM, it form the image and diffraction pattern that are magnified onto the viewing screen or camera. The objective lens is used to primarily focus and initially magnify the image. The specimen stage is inserted into the objective lens for imaging purpose. Basically, objective lens is put after the sample we choose information, and then effect of the lens we choose electron that are scattered in the lower angle, and use it to enhance the diffraction and mass contrast with a small one and enhance phase contrast with a big one. Then in this picture we see that when the parallel lines of the electron come to the specimen, the objective lens disperses the electron emerging from the back focal plane of the specimen, where the diffraction pattern found and recombine in the image plane, because there here the diffraction pattern found and then recombined their image plane to generate the high resolution image of atomic column. The focal length of the objective lens must be minimized to maximize magnification. Then the objective distance, or the distance between the specimen and the objective lens, must be very small. This is all about objective lens. In this slide, I will discuss about the objective lens and aperture. Objective lens aperture control the fraction of beam which is allowed to hit the specimen, and when all the light comes from specimen to the objective lens without optical objective aperture give this type of diffraction pattern, but when use a optical aperture only transmitter selected beam give a bright field image and give this type of diffraction pattern. And in this picture, when objective aperture apply like this give a low resolution and dark field image with single point of diffraction pattern, and the objective aperture put on like this give a high resolution and dark field image. In case of resolution of TEM, generally the smallest distance between 2 points that we can resolve is called the resolution. Resolution of human eye is 0.1 millimeter to 0.2 millimeter. Resolution of regular optical microscope is 0.2 micrometer. That a question is built there: what happen when a focused beam to the small spot? The focused spot not a get spot, this give a disk called airy disk. Because the reason we not get a single point of spot, because we can't convert to a beam to a smaller size than that its one wavelength. Here we see that the diffraction pattern and airy disk. In the first picture, we see that when the more parallel line comes and the large aperture give the parallel lines comes out of the aperture and not give any type of airy disk. But when the aperture size is small, give a coherent airy disk. After the single spot diffraction pattern, these diffraction patterns give a airy patterns of the airy disk. For an object consisting of single bright point object in dark background, the image produced by a perfect microscope according to the paraxial diffraction theory is the so-called airy disk, consisting of bright center spot like this and surrounded by series of rings. The intensity in a meridional cross section through the airy disk is the same for any aperture of objective or wavelength or light, but its wide varieties. In case of diffraction in 2D, the limiting factor of the resolution of the perfect light microscope. If two airy disks get too close, one can't resolve them. But according to the Relay criteria of resolution, 2 point source can just be resolved if they are separated in the image by distance del is equal to radius of airy disk. Here del is equal to resolution, mu is the reference index of the viewing medium, or beta is the semi-angle of the conversion of the magnifying lens. After the discuss about the resolution, I will discuss about the spherical aberration. In spherical aberration is a specific type of optical aberration. It occurs when a light rays passing through the periphery of the lens come to focus at slightly different location than the light ray passing through the center of the lens. Basically, this is decrease the image quality, and this aberration cured by adding the convex in the light optics. Another aberration is the chromatic aberration. In the chromatic aberration, a color distortion that occur when a lens can't properly reflect all the wavelength of color at the same point. Color aberration appear blurring or coloring of red, green like this, blue, yellow, purple around the edge of the image. It is caused by basically dispersion of the rays. Another deformity is the astigmatism. It occurs when the lens of the eye or abnormal shape. This is basically due to the abnormality in the lens shape caused distorted blurring vision. This is magnify the image produced by the object. The intermediate lens change the focusing position on the diffraction pattern or TEM image by adjusting its excitation. In the first intermediate lens magnify the initial image that formed by the objective lens. The lens can be focused on initial image formed by the objective lens or diffraction pattern formed in the back focal plane of the objective lens. In the same the picture that this is the intermediate lens present after the objective lens is the focal length is 105, and then the second picture see that the back focal length is 145, and the diffraction pattern is more better in this in comparison to the first one. In the second part of this video I will discuss about the scanning transmission electron microscopy. In scanning transmission electron microscopy, it is an advanced imaging technique then TEM that is used to visualize the structure and composition of material at nanometer to subatomic level. Basically, it provides a high resolution image and spectroscopic data by scanning by focus electron beam across a very thin sample and collect various signal in parallel. The most common signal acquired in STEM are bright field detector, annular dark field detector, and high angle annular dark field image. These detectors discussed in later slides. The technique commonly paired with energy dispersive X-ray spectroscopy and electron energy loss spectroscopy to provide correlative spectral map of elemental composition and electronic structure of this spectroscopy. Material prepared for STEM need to be electron transparent, meaning they allow electron to transmit through the sample with minimal scattering. This property enables a high number of transmission electrons to be collected by the different detector, thereby improving a signal to noise. Typical stem sample including tissue section, lamella, and nanoparticle on order of 100 nanometer thickness or less meet the criteria for the electron transfer. In this slide, we see that the interaction of electron with the thin sample elastically or inelastically in TEM imaging and inelastic in the ELS electron loss spectroscopy. In STEM, electron energy loss spectroscopy can be used to spectroscopically mapping the sample at atomic resolution. And in energy dispersive X-ray spectroscopy, basically when a electron from comes out ground state and the outermost electron come to the ground state generate the characteristic X-ray, or this is in a energy dispersive X-ray spectroscopy. In STEM, EDX is typically used for compositional analysis compositional analysis and elemental mapping of a sample, and backscattered electron use and secondary electron use in same imaging also. In the time objective and intermediate lenses after the sample, but in the stem, electron beam focus on sample 10 focus below the sample cause chromatic aberration due to varying electron energy being focused at different focal position. In the difference or similarities visit between TEM versus STEM, the main difference between STEM and TEM is the beam formation optics, which resulting different beam convergence angle at the specimen surface. In TEM mode, a parallel beam is desired. Alpha is 0 degree centigrade here, like this. See the parallel beam here. For STEM, a large value of alpha is needed in order to form a small localized probe on the small surface. Here, small angle is there and form a pointing probe on the specimen here. We see that the previous slide, the range of the incident angle determined by alpha become scattered according to the break scattering angle into cones, which cause the diffraction disk to form like this. Disk convey information regarding the crystallinity, structure, and symmetry within the specimen. The diffraction pattern in time will have the same symmetry, but will feature well-defined spot due to negligible range in alpha in case of TAM. In case of STEM, we see that different type of detector, bright field detector, annular dark field detector, or high angle annular dark field detector. A typical acceptance angle for bright field detector is half of alpha. BF stem or bright field stem image are analogous to phase contrast image in TEM and can provide high resolution information with enhanced contrast of the light element. Annular dark field detector ADF, yeah, annual dark field detector image are acquired using a ring shaped detector that surround the bright field detector. Basically, this is a ring shaped detector. Between is the bright field detector, and around that the annual dark field detector. That a large portion of the Bragg diffraction detector are collected. And the next one is after that bright field detector and annual dark field detector. We discuss high angle annular dark field detector. High angle annular dark field imaging is similar to annular dark field imaging, except only electron scattered to a very high angle of incident. This is like the theta 1 is the greatest one, high angle of diffraction in comparison to annular dark diffractor, or annular dark field detector is more diffracted in comparison to bright field detector. These are the references where I will take the information for these slides. And this is all about TEM and STEM. Thank you watching for this video. Happy learning.